Welcome again student into the 11th science chemistry class. Now in the last lecture I told you about the factors which affect the equilibrium constant. Now today we are learning the numericals based on equilibrium constant Kc. There is a problem number 12.5 into the textbook. The problem is in this way. Equal concentrations of hydrogen and iodine. Equal concentrations of hydrogen and iodine are mixed together in a closed container at 700 Kelvin and allowed to come to equilibrium. If the concentration of hydrogen iodide HI at equilibrium is 0.85 moles per decimeter cube, what are the equilibrium concentrations of hydrogen and iodine? If Kc, that is the equilibrium constant, 54 at this temperature. That means this equilibrium is given to us, equilibrium reaction, in which hydrogen and iodine are of equal concentrations. And the concentration of this HI is equal to 0.85 moles per decimeter cube. Given. Concentration of hydrogen iodide is given. Again, what are the concentrations of hydrogen and iodine? They ask us equilibrium concentrations of hydrogen and iodine. And what is given? If Kc, that is the equilibrium constant, is 54 at 700 degrees centigrade. Now, by applying the law of mass action to this equilibrium, what is the equation of Kc, that is the equilibrium constant? Kc is equal to concentration of products raised by its coefficient divided by multiplication of concentration of the reactants. Now suppose the concentration of hydrogen and iodine at equilibrium, suppose it is the x mole per decimeter cube, because both hydrogen and iodine are in equal concentration, because their initial concentrations of hydrogen and iodine are equal. So suppose the concentration of hydrogen and iodine which we have to calculate, suppose it is the x moles per decimeter cube at equilibrium. So on substituting all the values of Kc, concentration of Hi 0.85, but there is the bracket square as coefficient is 2 of this Hi. So here is the 0.85 bracket square. Concentration of H2 is x, we suppose that, and concentration of I2 is also x, iodine. Now x into x becomes x square. So 54 is equal to 0.85 square divided by x square. We have to calculate the value of x. So x square, x goes here, and this 54 gets divided here. So x square is equal to 0.85 into 0.85, because here is the square, divided by 54. But we want x only. So by taking under root of both sides, take the under root of both sides. So here is only x and here is under root of 0.85 into 0.85 divided by 54. You can solve this problem by using the logarithm table. Now see there the log of 0.85 and 0.85. Add the logs of 0.85 and subtract the log of 54 from it. And then again divide that value after this adding and subtracting, divide the value by 2, because we have to calculate the square root, and then see the that is the its you can see then the antilog of that by dividing 2 again, and the antilog you come here 0.12 moles per decimeter cube of the value of x. How we calculated? By seeing the log of the 0.85, we add the log of 0.85 and 0.85, same log will be there. then subtract the log of 54 from it and divide that value by 2 and see the antilog. Then you got this value. So X is the equilibrium concentration of both iodine and hydrogen. So the concentration of hydrogen and concentration of iodine is equal to 0.12 mole per decimeter cube. In this way, we can calculate the concentration of any one of the reactant or product if we know the value of Kc and remaining concentrations. So this type of problem will be there in the examination on the that is the equilibrium constant Kc. Now let us learn the very important law given by the scientist Le-Chatelier. What is that law and which are the factors which affects the equilibrium? We have to see that after this problem. Now let us learn a very important principle in chemistry. That is the Le-Chatelier's principle, the name of the scientist. He told about the equilibrium state and how the equilibrium state can disturb by the different factors such as concentration of the reactants or concentration of the products if increased. If concentration of reactant is increased or it may be decreased, again that is the temperature, pressure and catalyst also. Now these are the different factors which can influence or affect the equilibrium state, and how the equilibrium reaction, that is the reversible reaction which attain that equilibrium. Already equilibrium is attained of that reversible reaction, and how due to the different factors, their concentrations or their increase or decrease, how affects on that equilibrium state, and how the reaction again regain that equilibrium state, what the reaction have to do at that time. That means, for example, if any equilibrium reaction is there and it attains its equilibrium, we know that at equilibrium rate of forward reaction and rate of backward reactions are totally equal. And if at that time we again increase the concentration of the any one of the reactant, then what happen? The equilibrium get disturbed. That means the reaction again goes to the forward direction. Though there is the equilibrium is already attained, forward and reverse reactions are rates are equal. But if we increase the concentration of one of the reactant, again the rate of forward reaction get increases. Up to which or what stage? Up to that increased in concentration of the reactant get nullified or that get used up. That means if the equilibrium is attained by any reversible reaction, and if we do any change in concentration of reactant or concentration of product, then the reaction try to nullify. Nullify means reduce that effect which we or that change which we made during the stage of equilibrium. That means the reaction adjusts itself in such a way that it nullifies the change made, and again it got the equilibrium again by arranging itself. That reaction arrange itself. Now how it is happen? Now let's first learn the statement of the Le-Chatelier's principle, and then we'll see how the different factors influence on the stage of the equilibrium and how the reaction responds to that change, and how it again regain the equilibrium stage again. That means any change during the equilibrium can be nullified by that reaction and it again regain that equilibrium state. Now that is the Le-Chatelier's principle. Now let us learn the statement of the Le-Chatelier's principle. What is the statement? It states that when system means reaction, reversible reaction, at equilibrium, if the system is at equilibrium, reaction is at equilibrium, system means our reaction. So it states that when a system at equilibrium is subjected to a change, that system or that reaction is subjected to any change in any of the factors. That factors are pressure, temperature, concentration, etc. Subjected to a change in any of the factor determining the equilibrium conditions. That means that factor determines during the equilibrium, that factor determines the equilibrium conditions of that system. And that factors are, that is the optimum temperature or optimum pressure or optimum concentration. All these factors, if subjected or any one of these factors is subjected to any change during equilibrium, then the system will respond. Then the system will respond in such a way or in such a direction as or that to minimize or reduce or nullify the effect of change. That means that effect of change of pressure, temperature, concentration, etc. Then what is the statement? When a system at equilibrium is subjected to a change in any of the factor which determining the equilibrium conditions of that system means reaction, then the system will respond in such a way to minimize the effect of change. The system tries to minimize that change of that effect or that factors which affect the equilibrium. Now that is the Le-Chatelier principle. Now let us learn again influencing factors of Le-Chatelier principle. Now suppose first factor is which influence the Le-Chatelier principle, that is equilibrium, is that change of concentration. During equilibrium, if we change the concentration of any reactant or any product, then what happen? Let us learn. So first factor is or the influencing factor of Le-Chatelier principle is that change of concentration. Now consider a reversible reaction. Now formation of ammonia. What we require for formation of ammonia? NH3 gas, N2 gas, nitrogen gas, plus thrice H2, 3 moles of hydrogen, 1 mole of nitrogen, forms 2 moles of ammonia. Now this reaction is balanced reaction. 3 into 2, 6. Here nitrogens have the 2 atoms, hydrogen have the 6 atom. So twice NH3 means 2 nitrogen atom and 3 multiplied by 2, 6 hydrogen atom. Now this is the balanced reaction but reversible reaction, formation of ammonia. And again plus heat means heat is evolved. What this shows as heat is evolved, it is the exothermic reaction. Now the reaction proceed with decrease in number of moles. That means during the reaction or after reaction formation of product is there, that is the ammonia gas, but at that time the number of moles get decreases. And what is the delta N? That is the change in number of mole, that is equal to minus 2. How we calculated that? Now delta N, that is the change in number of mole, is equal to N2 minus N1. Now these N2 are the number of moles of product. How many number of moles of product? 2. And N1 are the number of moles of reactant. How many number of moles of reactant here? 3 plus 1, because nitrogen have 1 number of mole and hydrogen have the 3 number of moles. So 2 minus 1 plus 3 of nitrogen and hydrogen. 1 plus 3 means 4. So 2 minus 4 is equal to minus 2. That means after the reaction formation of product, what is there? The number of moles get decreased. Minus 2 means minus signs means decrease in number of mole, because the reactant have 4 number of mole but product have only 2 number of moles. We always calculated delta N as number of moles minus number of moles of reactant, number of moles of product minus number of moles of reactant. So again the forward reaction is exothermic. Why? Because heat is evolved. So because heat is evolved, so the reaction is exothermic. And for this reaction, iron, that is the main catalyst, is required, and small amount of molybdenum metal also required, but the main catalyst is the iron. And this process of formation of ammonia by using the catalyst iron at 700 degree centigrade, the temperature required for this reaction, optimum temperature is 700 degree centigrade temperature is required. And at that temperature or optimum temperature, what is there? 1 minute, few minutes, not the 700 degree centigrade, but suppose as the reaction is exothermic, it is less than 700 or any that is the optimum temperature will be there. Now again what is there? Now this process, when iron is the catalyst and small molybdenum is also there, and the formation of ammonia by this process, and this process is known as the Haber's process. Remember that. So ammonia is always synthesized by the Haber's process. Now at equilibrium, how we can write the expression of Kc, that is the equilibrium constant, and we know that at equilibrium what is there? The reaction quotient Qc and equilibrium constant Kc both are equal, because at equilibrium both the value of Qc and Kc are equal, and it is given as concentration of product divided by multiplication of concentration of the reactant. So here is the 2 number of moles of ammonia, so concentration of ammonia bracket square divided by concentration of nitrogen into concentration of hydrogen bracket cube, because 3 moles of hydrogens are there. Now in the first stage, what is there in the first stage? If we do any change, if we do not make any change in that reaction, then the system is always at equilibrium. But in the second stage, if we at equilibrium, if we disturb that equilibrium or change that equilibrium by making Qc less than Kc, that means if Kc is greater than the Qc, and if we disturb the equilibrium, then how we disturb? By adding hydrogen gas. That means when equilibrium is there, and if we add again the more amount of hydrogen gas, then the equilibrium get disturbed and Qc becomes less than Kc. The reaction proceed to the forward direction from left to right again. And due to addition of extra hydrogen, system is now no longer at equilibrium, because we add the extra hydrogen. Now the system is no longer at equilibrium, or no longer at equilibrium means there is no equilibrium because we added the extra hydrogen. Then how does the system regain its equilibrium again? How the system regain its equilibrium? Now we add the hydrogen extra, so the reaction proceed to the forward direction to nullify or cancel the effect of added hydrogen. That means the hydrogen get used up until the system attains its equilibrium. Now how it is attained? Now let us learn again. Now pay attention, students, again. Now what is the third stage? If we change the concentration of the reactant, then what happened? Now the added hydrogen, which we already add the extra hydrogen, this added hydrogen is to be used up. That means that added hydrogen used up which is extra we added during the equilibrium, that get used up and converted to more ammonia, because more and more ammonia formation will be there if we add the one of the reactants, such as that is the hydrogen, and restore the equilibrium again by using all the added extra hydrogen. There is formation of more and more ammonia gas, and the reaction again attain the equilibrium. That means equilibrium is restored again. In this way, Le-Chatelier's principle states that the reaction arrange itself by nullifying or by reducing the any change in that equilibrium stage and restore the new equilibrium again. Now, let us learn the stage 4. System, that means the reaction, respond to restore equilibrium. Always the reaction have response in such a way that it restore or again regain the equilibrium position. Thus, according to Le-Chatelier's principle, the effect of addition of this hydrogen or nitrogen or both hydrogen or nitrogen, if we add both or we add only hydrogen or nitrogen, what the system or reaction during equilibrium try to regain? Now it is reduced, that additional hydrogen or nitrogen or both of these gas is reduced by that system. And how it reduce? By shifting the equilibrium from left to right. That means forward reaction proceeds more and more, and the equilibrium is attained again, and the reaction arrange itself by shifting the equilibrium from left to right, so that the added hydrogen or nitrogen get consumed, and that is the forward reaction occurs to a large extent than the reverse reaction. To reduce that added concentration, the forward reaction occurs to a large extent than the reverse reaction, up to which state? Until the